This is Team 7, and our project is the Science and Engineering Complex Phase 4 construction. First, we'll introduce the project and the modeled activity, the collected data including time and equipment, give an explanation of the model, talk about model validation, the feasibility analysis, optimization, and the proposed solution. As I mentioned before, this project is the SEC Phase 4 complex on the University of Alabama campus. Prep work started in May of 2011 and site completion is expected in May of 2013. Here you can see an aerial of the project and the modeled activity. Haul routes 1, 2, and 3 are labeled, as well as the locations of the gravel and soil stockpiles. In this photo you can see more clearly the haul roads. This is the time data we collected for the activities on site, which were used in the EasyStrobe model.
There are three types of equipment that were used in our model. The backhoe is a Hitachi Z-Axis 350 LC. It has a capacity of 2.7 bank cubic yards. The truck is a Cat D 250E with an average haul capacity of 14 loose cubic yards. Lastly, the wheel loader is a Cat 600 with a capacity of 4 loose cubic yards. The explanation of our model shows the process starts by loading the soil into the truck with the backhoe. The truck then hauls the soil through the space constraints and dumps the soil on the backside of the project. The truck is then loaded with gravel and goes through its original starting point and continues to travel on haul 3 and dump the gravel in the desired spot on the project site. Finally, the truck returns to its original position and the cycle starts over again.
In order to validate the model, we compared the actual measured task times with the modeled predicted times. Then we compared the percent difference between the two. Finally, we compared the percent difference for soil and gravel for production. For the feasibility analysis, we chose different scenarios to test in order to find the best production and unit cost. We found that adding one truck would increase production. In order to increase production and keep unit costs low, adding one truck would be the best option. Even though it shows the same unit cost with the space constraints removed, the cost doesn't take into consideration the price to remove the space constraints. This issue could have been addressed prior to the start of this activity.
This is one of our optimized models created after the feasibility analysis. It was found that if we have 2 trucks as opposed to 1 truck, we get double the production. Shown here in this optimization model of a different scenario, it was also found that if we increased our number of trucks to 4 and eliminated all of our space constraints, we would have our maximum production. This graph represents our production versus the number of trucks. As you can see, if we only eliminate space constraints 1 and 2, then we have the same production as if all the space constraints were still present. However, if space constraint number 3 is removed, production increases. Also, removing all the space constraints yields the same result. This is another optimization table that includes production variance, duration variance, and cost variance for each of the presented scenarios. Our proposed solution from a cost viewpoint is to add one more truck to increase production. If we look at these scenarios from a production viewpoint, then adding 3 trucks and removing all space constraints is our best option. If you have any comments, please make them now. Thanks for listening.